Hi, I'm Matteo, editor of this episode of Synthesis Workshop. In this episode of the thematic series of Advanced Organic Chemistry course, we are going to touch the transition metal catalyzed CH functionalization reaction with Joshua Paolillo. Joshua achieved his bachelor degree at the University of Connecticut under the supervision of Professor Nicholas Lett, studying oxidation reactions enabled by oxammonium salts and photoredox catalysis. After a 2 years experience at Boehringer Ingelheim, he joined the group of Marvin Parasram at NYU as a PhD student, studying the excitation of nitroarenes and their applications in organic synthesis. Joshua has been already a guest speaker of our podcast, and if you are interested to the photochemistry of nitroarenes, I invite you to check that talk as well. And with that, I'll leave the stage to Joshua.
Thank you for the introduction and for the opportunity to contribute to this series. Today, we will be covering transition metal catalyzed CH functionalization. Let's start by taking a look at what will be covered in this lecture. First, we will start off by going over general concepts and terminology of CH functionalization. Next, we will look at what factors impact the site selectivity of CH functionalizations and the strategies chemists have used to achieve site selectivity in CH functionalization methods. Finally, we will look at examples of catalytic CH functionalizations for both carbon-carbon and carbon heteroatom bond formation. Directly functionalizing a CH bond presents an efficient way to introduce functional handles and greater complexity into a molecule. However, the high thermodynamic stability of most CH bonds makes them relatively unreactive, and since organic compounds often contain multiple similar CH bonds, achieving site selectivity is difficult. Thus, historically, CH functionalization was not viewed as a practical transformation in organic synthesis. However, advances in our understanding of organometallic chemistry over the last few decades has changed this view, and chemists have been able to develop many methods for the selective functionalization of CH bonds into a wide range of functional groups, even in the presence of more reactive functionalities. As a result, CH functionalization has become a powerful and widely used strategy in organic synthesis. In today's course, we will not go over a comprehensive list of all the different CH functionalization reactions known, since the number is quite large. Instead, we will focus on building an understanding of the mechanisms by which these transformations occur and the strategies that have been employed to overcome reactivity and selectivity challenges. Let's first go over the definitions of some terms that will come up throughout the lecture. CH functionalization refers to the overall transformation of the replacement of a CH bond by another element or functional group. CH activation specifically refers to the CH bond breaking event and is defined as the cleavage of a CH bond that occurs through an interaction with a transition metal, resulting in the formation of a carbon-metal bond. This is an important distinction to make, because as we will see on the next slide when we discuss the mechanisms of CH functionalizations, not all of them involve the formation of an organometallic intermediate. The mechanisms of transition metal catalyzed CH functionalizations typically fall in one of two general mechanistic categories: inner sphere mechanisms and outer sphere mechanisms. Inner sphere mechanisms are mechanisms that go through a CH activation event where an organometallic intermediate is generated. This is the same type of organometallic intermediate that is generated during cross-coupling reactions, and as such can be intercepted by a wide range of reactive partners to functionalize the carbon. Seen here are the major categories of CH activation that have been established and which metals are typically associated with them. On the next slide, we will take a more in-depth look at inner sphere mechanisms and how factors such as the metal, ligands, and reaction conditions impact CH bond activation. Outer sphere mechanisms, on the other hand, are mechanisms that do not involve a CH activation event and thus do not go through an organometallic intermediate. These mechanisms break CH bonds through either radical or concerted means. In radical-type mechanisms, a hydrogen atom abstraction event generates a carbon-centered radical that is subsequently functionalized. Concerted-type mechanisms operate through CH bond insertions, where the species bound to the metal directly inserts into the CH bond to generate the functionalized product. We will see examples of both inner sphere and outer sphere mechanisms later on when we discuss specific types of CH functionalization reactions. On the previous slide, we saw 4 general classes of CH bond activation for inner sphere mechanisms and which metals were typically associated with each. But not only does the identity of the metal play a role in the mechanism of activation, but also the identity of the ligand. If the ligands bound to the metal are bifunctional and contain an additional Lewis basic heteroatom, such as phosphine oxide or carboxylate ligands, they can assist in the CH bond activation step. This is known as concerted metallation deprotonation, abbreviated as CMD, or amphiphilic metal ligand activation, abbreviated as AMLA. CMD refers to any process where the metal-carbon bond forms as the CH bond is deprotonated, while AMLA specifically occurs through a 6 or sometimes a 4-membered transition state, and in both cases, CH bond activation occurs without changing the oxidation state of the metal. In this example by the Strassner group, we can see how this interaction between the ligand and the CH bond impacts the mechanism of CH activation. When comparing potential transition states for the CH activation of methane by a bis-NHC palladium complex, we see that the transition state for AMLA was calculated to be much lower in energy than the transition state for oxidative addition, highlighting the ability of the ligands to impact the reactivity of a catalyst for CH activation. Now that we have seen how transition metals can activate CH bonds, we will look into some of the principles that dictate site selectivity of CH bond functionalization. We will start off by going over which types of CH bonds are reactive under which types of mechanisms. Outer sphere mechanisms are generally most reactive towards CsP3H bonds since they have lower bond dissociation energies than CsP2H bonds and form more stable radicals after homolytic bond cleavage in the case of radical mechanisms. Conversely, activation of CsP3H bonds is generally more challenging for inner sphere mechanisms. Although CsP2H bonds are stronger than CsP3H bonds, since we are forming an organometallic intermediate, we must also take into consideration the strength of the carbon-metal bond that forms, and generally, sp2 carbon-metal bonds are stronger than sp3 carbon-metal bonds. Selectivity for inner sphere mechanisms is also impacted by the method of CH activation, as different mechanisms will be selective for the most electron-rich CH bond or the most electron-poor CH bond. For example, more acidic CH bonds will undergo faster CMD. Sterics can also be harnessed as a powerful tool for site selectivity through catalyst control. Bulky ligands around the metal center can disfavor reactivity at sites that are electronically reactive but sterically hindered. In the first example shown here of a CH borylation reaction using a bulky iridium catalyst, borylation only occurs at the least sterically hindered site. In some cases, steric hindrance can even override innate reactivity. For example, in this rhodium catalyzed reaction, which operates through an outer sphere mechanism, the secondary benzylic site should react faster than the primary benzylic site since it has a lower bond dissociation energy. However, the immense steric hindrance around the metal center results in reactivity at the primary site instead. One thing to keep in mind is that steric effects can only influence selectivity between 2 or more reactive CH bonds, but cannot make an unreactive CH bond reactive towards the catalyst. One of the most common strategies for achieving site selectivity in transition metal catalyzed CH functionalization is the use of directing groups. Directing groups are most commonly used for inner sphere mechanisms and operate by bringing the metal catalyst in close proximity to the desired CH bond through the formation of an agostic complex, which gives precise control over which bond is activated. Many different directing groups have been developed for both CSP2 and CSP3 H-bond functionalization methods, and some even enable enantioselective transformations. In the case of CSP3H functionalizations, the use of a bidentate directing group results in more efficient CH activation and prevents unwanted beta hydride elimination. Now that we have gone over the factors that affect site selectivity in CH functionalization, let's move on to discussing the various types of transformations that can be accomplished through CH functionalization. We will begin by looking at the CH functionalization methods for the formation of carbon-carbon bonds. Carbon-carbon bond-forming reactions are some of the most powerful reactions in organic synthesis, and many transition metal catalyzed methods have been developed to functionalize CH bonds with a wide range of coupling partners for CC bond formation. Generally, these reactions operate through catalytic cycles that are similar to those seen in traditional cross-coupling reactions, including an oxidative addition step and a reductive elimination step. However, for CH functionalization, there is also a CH activation step, and depending on the mechanism of CH activation, it can occur either before or after oxidative addition. Shown here are some examples of CH functionalization methods for carbon-carbon bond formation, including intramolecular and intermolecular carbon-carbon bond forming reactions. Another CH functionalization reaction that forms carbon-carbon bonds is the oxidative Heck coupling, though, unlike the examples we just went over, the oxidative Heck coupling requires the addition of an external oxidant in order to make the reaction catalytic. To see why, let's examine the proposed mechanism for the example shown here. It starts with the substrate undergoing CMD with a palladium-2 catalyst to generate a palladium-2 organometallic intermediate. Migratory insertion, followed by beta hydride elimination, furnishes the desired functionalized product and a palladium-2 hydride, which undergoes reductive elimination to generate palladium-0. Thus, in order to turn over the catalytic cycle and regenerate the active palladium-2 catalyst, an oxidation step is required. CH functionalization can also be utilized to form CN bonds through CH amination reactions. In CH amination reactions, the carbon being functionalized undergoes a formal oxidation, and, like we saw with the oxidative Heck reaction, an oxidant is required in order to make the method catalytic. However, oxidants aren't required in cases where the nitrogen source for the reaction is pre-oxidized, which we will see when we go over specific examples. CH amination can occur through both inner sphere and outer sphere mechanisms. Inner sphere mechanisms have similar catalytic cycles to Buchwald-Hartwig CN coupling reactions, where CH activation generates an organometallic intermediate, followed by coordination of the nitrogen to the metal center, and then CN reductive elimination to generate the desired CN coupled product. Subsequent oxidation turns over the catalytic cycle by regenerating the active catalytic species. Due to the polarized metal-nitrogen bond, the energy barrier for CN reductive elimination is often higher than that of CC reductive elimination, and therefore it is not uncommon to see the oxidation step prior to CN bond formation, since reductive elimination occurs more readily from metals in higher oxidation states. Outer sphere mechanisms typically involve metal nitrenoid species that functionalize CH bonds either through concerted bond insertion or stepwise radical pathways. Shown here are three general classes of CH amination reactions. Oxidative CH amination reactions utilize simple amine or amide coupling partners and require an external oxidant to turn over the catalytic cycle. Electrophilic CH aminations are methods that utilize pre-oxidized nitrogen sources and thus avoid the need for an external oxidant. A few examples of common pre-oxidized nitrogen sources are shown here, such as N-haloamines, azides, and oximes. Insertion reactions go through metal nitrinoids that are generated by the reaction of a transition metal with either an amine and an oxidant or a pre-oxidized nitrogen source. Since insertion reactions operate through outer sphere mechanisms, they tend to be selective for the weakest CH bonds in a molecule, as demonstrated in the example shown here, where the metal nitrinoid generated by the reaction of the ruthenium catalyst with the sulfonyl azide selectively reacts at the benzylic site. CH functionalization reactions have also been developed for CO bond formation. Like with CH amination reactions, the carbon being functionalized undergoes a formal oxidation, and an oxidant is required for the method to be catalytic. Typically, for CH oxygenations, the oxidant also serves as the oxygen source for the reaction. CH oxygenation can occur through both inner sphere and outer sphere mechanisms. Inner sphere mechanisms typically follow a general catalytic cycle where the substrate undergoes CH activation with the active catalytic species to form an organometallic intermediate, which is followed by oxidation by the oxidant and then CO reductive elimination, which produces the oxygenated product and regenerates the active catalyst. Outer sphere mechanisms generally utilize high-valent metal oxo species that are able to homolytically cleave CH bonds through hydrogen atom abstraction to generate carbon-centered radicals. Oxygen transfer to the carbon-centered radical occurs via radical rebound with the metal oxo complex to produce the oxygenated product. Here we can see some examples of CH oxygenation reactions that have been developed, and some of the common oxidants employed in these transformations, such as molecular oxygen, peroxides, and hypervalent iodine reagents. Oxidative inner sphere mechanisms can be used to oxygenate both sp2 and sp3 CH bonds, while metal oxo complexes have become powerful catalysts for C-sp3H bond oxygenations. In this example of a CH hydroxylation reaction developed by the White group, high site selectivity was achieved by employing an electron withdrawing group to deactivate the more proximal methylene CH bonds, resulting in a selective hydroxylation at the more distal tertiary site. Now, let's take a look at some applications of CH functionalization by highlighting examples where CH functionalization was used in the synthesis of natural products. The Riesman group utilized a directed CH alkylation reaction to strategically form a key carbon-carbon bond during the enantioselective synthesis of a cytotoxic natural product. Another example by the Tokuyama group used an intramolecular CH alkylation reaction to form a key 9-membered ring intermediate for the synthesis of a hexacyclic alkaloid natural product. Before we conclude this lecture, I will quickly go over some of the other types of CH functionalization reactions that have been developed, but that I did not have time to go over in more detail. Methods for CH borylations have been developed for the construction of aryl and alkyl boronic acids and esters, which are highly valuable reagents for cross-coupling reactions. These transformations typically use iridium or rhodium-based catalysts that go through metal 3,5 or metal 1,3 catalytic cycles. CH halogenation reactions operate through similar mechanisms to CH amination and oxygenation, though the field has mostly been limited to palladium-catalyzed methods. Photochemical and electrochemical CH functionalizations have been emerging as powerful CH functionalization strategies, since they allow for many of the same reactions we discussed earlier to be conducted under much milder conditions, and are currently highly active fields of research. While we covered a lot of material in this lecture, it is by no means a comprehensive overview of the entire field of transition metal catalyzed CH functionalizations. Listed here are reviews and studies for further readings on this topic. I would like to again thank Matt for the opportunity to contribute to this series, and I hope this lecture has helped you develop a foundational understanding of transition metal catalyzed CH functionalizations.
Thank you, Joshua, for your great talk about metal catalyzed CH activation chemistry, a very useful strategy for the direct functionalization of inert CH bonds. This was the last episode of the Transition Metal Catalysis module. Tune in for the next part of this project as we continue our advanced synthesis course covering the field of asymmetric catalysis. Thank you for watching and see you next time.